Hello everyone, welcome to Benji Physics. This is me Bandar Bit. In our today's video, we're going to talk about uniform angular displacement. You and I will go through different examples that illustrate the physics behind uniform angular displacement and how to calculate it. A real-world example for uniform angular displacement could be found, for example, in the motion of the moon while it's rotating the Earth. Or another example could be orbiting satellite around the Earth. However, our question in this video here today is, what is uniform angular displacement and what does it measure? Well, before we answer that question, let us first see how uniform angular displacement happens. Uniform angular displacement happens when an object moves around a circular path. And when this happens, the angle of the body with respect to its initial angular position changes. So we use angular displacement to calculate the position of the object that moves around the circumference of that circle. In mathematics and physics, angular displacement denoted by the Greek letter theta. You might be wondering why we call it uniform or uniform angular displacement. The word uniform means constant, and the reason why we call it uniform goes back to the constant speed of every object that moves in a circular path. For example, this dot here moves with constant speed and covers the same angular displacement each second. So we have constant rate of change in angular displacement. Also, as you see here, we have two arcs that have the same length. So that's why we call it uniform. But pay attention, I said constant speed, not constant velocity, because the velocity here is changing. But how is that? Well, the velocity is changing in the direction. As long as the dot here moves in a circular path, then the direction changes every second. The yellow arrow here shows the changing direction, and that's why the velocity is accelerating or changing. The standard measurement unit of angular displacement is radians, and denoted by rad. And to calculate the change in angular displacement, we use the angular displacement formula, which is delta theta is equal delta S over R, where delta theta is the change in angular displacement measured in radians, and delta S is the length of the arc measured in meters, and we have R here is the radius of the circle also measured in meters. And when theta or angular displacement is equal to 1 radian, then the length of the arc S is equal to the radius of the circle. For example here, the length of the arc S is equal to the length of the radius. So 1 radian means the length of the arc is equal to the radius of the circle. One notice that I should highlight here is that radians are commonly written in terms of pi. The angle in radians for a complete circle is equal to 2 pi times r over r, which is equal to 2 pi. To convert angle in degrees to angle in radians, we multiply angle in degrees by pi over 180. Let's say that we have example here. We have an object that moves in a circular path and stops at a specific angle. So let's say that this dot here moves along the circumference of this circle and stops at 90 degrees. So to get delta theta here, we multiply 90 degrees by pi over 180. So that will equal 1.57 radian or pi over 2. So in this example, we have angle in degrees. We convert it to radians to get delta theta. But what if we have the length of the arc but we do not have angle in degrees? Then we use the main formula. For example here, let's say that this dot here moves along the circumference of this circle and create an arc, which has a length of 20 meters, and the radius of the circle is equal 7.64 meters. So to get delta theta here, we use the main formula as long as we have the radius and the length of the arc. So delta theta here is equal to delta S, which is 20 meters, over the radius, which is 7.64. So this will equal 2.61 radian or 5 multiplied by pi over 2. Now we have come to an end for the angular displacement part, and in the next part we will talk about angular velocity and how to calculate it. One last thing, your likes and support will encourage me to do more videos like this. So if you like my explanation, hit like and subscribe to my YouTube channel so that you get to see the next upcoming videos. Thank you.